Hello everyone. Thank you for being here and watching this video. I'm Hossein Golestani, and in this video, I'm going to present our paper in this year's ICS, which is Calipers, a criticality-aware framework for modeling processor performance. I've done this work with Rathijit Sen, Vinson and Gagan Gupta, who I had the chance to work with in my internships at Microsoft. So without further ado, let's get started. Designing a processor architecture has two fundamental aspects, which are instruction set architecture or ISA design and microarchitecture design. An architect may have to choose a specific technique out of many possible techniques and may have to make specific design decisions at each step of ISA and microarchitecture design from the very beginning to later evolutionary cycles. Benefits of techniques and design decisions are not always obvious because of the complex interactions that exist among processor components, as we see in this sample processor pipeline. So processor designers need a tool that effectively models complex architectures to evaluate their design decisions by analyzing the performance and bottlenecks of their designs. The most commonly used processor design aid is cycle-accurate simulators. Cycle-accurate simulators can provide fairly accurate performance or execution time of a program running on a model processor in cycles. But there are also many other tools with different capabilities. For example, instruction set simulators are faster than cycle-accurate simulators, but can only count the total number of instructions executed. Mechanistic models can also be fast and estimate performance penalties using hand-constructed analytical models. FPGA emulators and circuit simulators are greatly accurate, but take an extreme amount of effort to develop. A common characteristic of these tools is that they typically offer limited or no options for tuning the accuracy as well as the speed. More importantly, a major issue is that it is not straightforward to gain deep insights on the design using the analysis report or statistics that these tools provide, meaning that the exact bottlenecks of a design may not be comprehensible from the reported numbers. Some of these tools provide cycles per instruction or CPI stack, giving a breakdown where cycles are spent, but it is in aggregate or averaged over the whole program. Additionally, exploring the design space or evaluating what-if scenarios using such tools may not be effectively or easily done, and often requires modeling or implementing the design choices. So these challenges are basically the motivation to our work. We would like to have a tool that provides deep insights on the bottlenecks with reasonable speed and at desired accuracy, and can explore design ideas and what-if scenarios with low effort. In this work, we propose calipers with the challenges just mentioned in mind. Criticality awareness is of paramount importance in the design of calipers. So one of the main features of calipers is insightful analysis of processor bottlenecks. We would also like to have a processor model with flexible fidelity so that designers can have a wide choice of accuracy. And last but not least, calipers should allow easy design space exploration at any point in this spectrum. Calipers achieves these features by graph-based modeling, that is, modeling a program's execution on a given architecture using an event dependence graph. Insights on the bottlenecks are obtained by finding the critical paths in the graph and their components. And finally, design space exploration is facilitated by manipulating the graph, which can be done in a relatively straightforward way. Let's take a quick look at how calipers works. Calipers takes the program's dynamic instruction trace, microarchitectural specifications of the processor, and a cost table as inputs from the user. It builds a graph-based representation of dynamic microarchitectural events based on different types of dependencies between them. The cost table determines the weights of the edges of the graph, or actually the latency of different events. Some costs are deterministic, such as pipeline interstage latencies and latency of execution units. But latencies of instruction and data memory accesses may be non-deterministic, mainly due to the cache hierarchy. The cost table specifies the particular model that should be used to obtain such non-deterministic costs. Once the graph is constructed, graph analysis is performed to address the questions of the designer. By applying graph algorithms like longest path search, total execution cycles and instruction level parallelism can be computed. The composition of the longest path or the critical path shows the breakdown of the bottlenecks. Analyzing secondary critical paths can help the designer understand to what extent a specific component in the primary critical path is worth optimizing. Also, by adjusting graph edge weights or manipulating graph vertices, various what-if scenarios can be modeled and explored without rerunning the program. Here are the highlights of what we have done with Calipers. We have modeled in-order and out-of-order execution in conventional as well as data flow architectures. Calipers has achieved relatively to highly accurate results based on the fidelity of the inputs used to build the graphs. We also introduce vectorized graph analysis by representing design parameters and graph edge weights as vectors. This enables simultaneous modeling of multiple configurations, which results in rapid design exploration and linear speedup. We have done bottleneck analysis on RISC-V and edge architectures, as well as real-life what-if scenario studies that designers may face. And lastly, the open source implementation of Calipers is available at the shown repository. This is the outline for the rest of this presentation. First, I described modeling details in the graph-based representation. The accuracy and performance of Calipers are discussed next. Then I present some sample bottleneck and what-if analyses before concluding. As I mentioned earlier, Calipers models the execution using an event dependence graph. A vertex in the graph denotes a particular microarchitectural event that a dynamic instance of an instruction undergoes. For example, for the multiply instruction shown on the right, there are 3 events: fetch, execute, and commit. More vertices or events may be defined for higher modeling accuracy or flexibility. The edges in the graph denote ordering dependency between the events, and the edge weights model the delay or minimum latency lag between them. Ordering arises from essential microarchitectural characteristics like different stages in the pipeline or from data control and structural hazards. The example in this slide just shows pipeline ordering. We will see examples of other types of dependencies in the following slides. But before that, note that graph-based representation of microarchitectural events has been around since about 2 decades ago. As we will see, we introduced various novelties on top of prior work. For example, vertices and edges and their weights can be modified in Calipers to explore design variants or techniques. This requires modeling dynamic resource conflicts and scheduling, which Calipers can do. Calipers also expands the options for the types of inputs used for building the graph. And in addition, Calipers can perform vectorization in the graph for rapid design exploration. Let's see how the graph-based representation of events can provide insights with an example. Assume we have a data cache that takes 5 cycles and a miss, and has only 1 miss status handling register or MSHR with 1 cycle for registering a request. Also, assume we have a 5-cycle multiplier and a 1-cycle adder. The first instruction loads a value from memory, and we can see the events for it here. Note that here we have used the vertex type for the memory stage. Assuming the load was a miss in the cache, the weight of the edge from M0 to C0 denotes 1 cycle for MSHR registry plus 5 cycles for reading the missing value. The next instruction is another load. And assuming it is also a miss, the edge weights are similar to the previous instruction. But since there is only one MSHR, there is a structural hazard here shown by the edge from M0 to M1, meaning that the second request is blocked until the first one vacates it. The next instruction is a multiply with the vertices as shown here. Since this multiplier reads R1, there is a data dependency to the first load shown by the edge from M0 to E2. The final instruction is an add with these vertices. And we have another data dependency here between the multiply and the add, which is shown by the edge from E2 to E3. A designer may consider optimizing the multiplier because it takes almost as a load miss. But let's see if it will be effective. Graph analysis shows that there are two critical paths in the graph with a length of 15. If the multiplier is optimized to take 2 cycles instead of 5, there will still be a critical path of length 15. This optimization doesn't work because of the structural hazard introduced by the single MSHR. Now, if we have another MSHR, the resource dependency between the two loads is broken, and we will have an optimized critical path of length 12. As we can see, the graph-based representation provides more insights in comparison to conventional performance analysis numbers. Calipers needs to model various aspects of a processor as shown in this long list. In general, pipeline, data, control, and resource dependencies, as well as the related latencies and bandwidths must be taken care of. Specifically, issuing instructions, considering the limited number of execution units and queue entries must be modeled properly. Non-deterministic events like memory accesses and branch prediction are also of particular importance. I'll touch on some of the more important aspects in the next few slides, but for a detailed discussion on these aspects, please refer to our paper. Okay, issue order and latency are modeled by adding appropriate edges between the execute vertices of instructions in calipers. How or when instructions are scheduled to be issued in a processor depends on the processor architecture and data and resource dependencies between the instructions. Let's take a look at an example. Assuming there is data dependency from instruction I0 and I1 to I2, edges from E of I0 and I1 are added to E of I2. In the case of an in-order core, instructions are issued in order. In-order issue is modeled by an edge with the weight of 0 as shown on the left between E of I0 and E of I1. Since there is already an edge between E of I1 to E of I2, no additional edge is needed. So how does Calipers obtain a scheduling order, particularly for an out-of-order core, to model contention of instructions on finite resources? Our solution is to first build the base graph for a sliding window of instructions that accounts for control and data hazards, and then calculate the length of the critical path to the E vertices. Instructions are in fact issued and scheduled to use the resources using the list of the E vertices sorted based on their critical path length. Then edges are added to model the order by which instructions use the limited execution resources. Finally, the critical path is updated to account for these newly added edges. The complete algorithms for instruction scheduling and modeling structural hazards, as well as their time and space complexities, are discussed in the paper. So please refer to the paper for more details. But let's take a look at an example to see how this process may affect the critical path. Assume that there is a single multiplier with 3-cycle latency and I3, I4, and I5 are multiply instructions. The numbers on the left side of the vertices show the length of the critical path to them, which is the basis for scheduling. So in this example, I3 has the least priority to use the multiplier. The red edges are added to impose the order by which these instructions occupy the multiplier. As we can see, adding these edges have increased the critical path length to I5 and I3. Control and data speculation, which are related to branch and value prediction respectively, are performed in model processors for better performance. These are modeled by appropriately inserting or removing edges between the speculated and the dependent instructions. As an example, let's take a look at how branch prediction is modeled. For a correctly predicted branch, there is an edge from the fetch vertex of the branch to the fetch vertex of the next instruction as shown on the left. For a mispredicted branch, on the other hand, this edge is sourced from the execute vertex of the branch as shown on the right. This means that the processor has fetched the right instruction after it detected a misprediction once execution of the branch was completed. Misprediction might increase the length of the critical path, which is shown by the red edges. Here, critical path gets longer with an amount that equals to the execution cycles of the branch plus the difference between the fetch cycles of the next instruction in the two cases. Fetch cycles of the next instruction is often longer in the case of misprediction because an I-cache miss following a misprediction is quite probable. For modeling branch prediction, Calipers needs to know the branch prediction outcome. And for loads, stores, and instruction fetch, Calipers needs to know the memory access cycles. As I mentioned earlier, these are dynamic information. Such information can be obtained from various models that can be integrated into Calipers, like statistical, analytical, and functional models. Alternatively, this information may be captured from external tools like existing simulators or even real hardware and provided along with a trace. In fact, Calipers can take advantage of various sources based on their availability. For example, when a simulator or real hardware is unavailable during earlier stage design exploration, simple models may be used. From another point of view, these choices enable a trade-off between fidelity of Calipers and speed or amount of effort needed to leverage more sophisticated sources. Okay, let's move on to experimentation with Calipers. We have evaluated the accuracy and performance of Calipers and performed various bottleneck and design studies. We have leveraged different RISC-V and edge processor models with the details shown on the slide. Spec benchmarks with reference inputs were used as our test programs. We validated Calipers' accuracy for the RISC-V ISA against Gem5, which is a widely used cycle-accurate simulator. We matched the Calipers and Gem5 core models by properly setting the model parameters. I-cache and D-cache access cycles and branch resolution outcomes were captured from Gem5 and fed along with a trace to Calipers. The CPI or cycles per instruction of the different programs are shown in this chart. As we can see, CPI difference is quite small in both the in-order and out-of-order core models, 1.7% and 4.8% respectively. Alternatively, instead of using the recorded information from Gem5, we use the functional memory model and a stochastic branch prediction model of our own. This approach resulted in 9.5% CPI error for the out-of-order model. So using lower fidelity inputs can increase the error, but the accuracy is possibly within an acceptable range, particularly for earlier stage experiments when accurate inputs may be unavailable. As for the performance of calipers, we again compared it with Gem 5. Calipers is at least 50% faster than Gem 5 when actually trace generation is not included in the time measurement of calipers. An interesting feature of calipers is that it can simultaneously model and analyze multiple configurations using vectorized edge weights. Using vectorization, calipers doesn't need to construct a graph from scratch in n separate runs or actually using n separate threads of execution for n configurations. This results in almost linearly scaling calipers' speed with the size of the vectors, each element of which corresponds to a particular configuration. As we can see in the chart, calipers' speed can be improved by an order of magnitude or even more when enough configurations are modeled simultaneously. Okay, let's see how calipers can aid real-world design studies. Once the critical path is identified, the breakdown of the cycles in it provides insights on bottlenecks and candidates for optimization. The breakdown of the bottlenecks results in charts like the one shown in this slide. Such charts can be studied for hours, but I just highlight one observation from this sample chart. There are several benchmarks such as DeepSjang, Exchange2, and GCC where the front end is a major bottleneck. These programs, rather than all the programs, can benefit from optimizing fetch and branch prediction. Moreover, in these programs, front end is more of a bottleneck in the out-of-order core in comparison to the in-order core. This is actually because the out-of-order core fetches instructions more aggressively to keep the pipeline busy as there is no in-order issue constraint. Also, decode and dispatch cycles are more conspicuous in the out-of-order core due to the complexities like register renaming. Let's take a look at a design study for the RISC-V core. We investigated how adding criticality awareness to value prediction can improve its effectiveness. Value prediction has been proposed to enable instructions continue execution even before the source data, particularly from an earlier load, is available. Value prediction can be easily modeled in calipers by removing data dependency edges. Since value prediction demands chip resources, not all loads may be value predicted. So the design question here is that what fraction of loads should be value predicted? Also, do some loads provide more benefits than others when value predicted? As for choosing the loads to be value predicted, we modeled two spectra of efforts in prior work. One is criticality-aware that has no regard to criticality and targets raw coverage, which is defined in the box. The other is criticality-aware that prioritizes predicting loads that are in the critical path. We can see the performance improvement of the two approaches at different fractions of covered loads in this chart. In the criticality-aware approach, as more loads are chosen randomly and value predicted, the performance improves almost proportionately. In the criticality-aware approach, the main, secondary, and tertiary critical loads are value predicted first, and the remaining loads are covered based on their latency. As we can see, this approach results in achieving most of the possible performance improvement at lower load coverage. The chart has been marked with data points of a state-of-the-art work related to the two approaches. In particular, for focused value prediction, which focuses on the critical loads but can only predict a fraction of them, we see a similar performance improvement is possible at just about 5% of coverage. So all in all, this study reveals that much more potential is still there using much more focus on critical loads. Let's take a look at another design study, this time for the edge architecture. The block structure of the edge ISA presents an opportunity to organize instructions within a block to simplify the decode logic. Each edge instruction is made up from a 16-bit base and additional optional bytes. The 4-segment and 2-segment formats, as we see on the slide, simplify instruction decode by packing the base of instructions in one segment. The 4-segment format leverages even more segmentation, as shown on the left. In the contiguous block format, instructions are organized linearly, as we see on the right. The effect of different block formats is modeled by adjusting decode edge weights in the graph in Calipers. The trade-off that we want to study here is that while the segmented formats simplify decoding, they may delay availability of instructions to when their additional bytes are decoded. On the other hand, the contiguous format doesn't have this issue, but it requires a more complex decoder. The performance with different block formats is shown in this chart. There is little difference between the 4-segment and 2-segment formats. For the contiguous format, we consider two cases. One is assuming the decode logic has no impact on clock frequency, and the other is the decode logic requires an additional cycle. When there is no impact on the clock, the contiguous format provides 4.6% performance improvement, which is due to the sooner availability of earlier block instructions. On the other hand, when there is the extra penalty cycle, the contiguous format degrades the performance. So there is this interesting trade-off here. If the designer wants to adopt a contiguous block format, they need to optimize the decode logic so that there is no additional decode cycles, and the advantage of this format can be fully realized. Okay, let's move on to the conclusion. So Calipers models the program execution on a processor using an event dependence graph whose edge weights can be vectorized. We saw that Calipers can use various cost models to build the graph at desired accuracy and enable rapid design space exploration. We also saw how the breakdown of bottlenecks by Calipers provides insights on the design and how straightforward adjustments to the graph can enable various ISA and microarchitecture studies. Please refer to the paper for more details and discussion on modeling the leverage algorithms and other design studies. Thank you very much for your time and for watching this video. I hope you enjoyed it.